So, hello everyone, and welcome to the next session of our Digital V-Days. I'm happy to say hello to all of you and that you took the time to participate in our webinar session today. Today's topic is board-to-board connectors in high-speed signal chains. And our referent, our speaker today is Baptiste Bouix, who is working as a product manager specialist for data transmission at Würth Elektronik. He will hold today's webinar and also answer all your questions at the end of the webinar. So you will be muted during the webinar, but nevertheless, you can ask us your questions with the Q&A function, and you will find that on the lower right-hand side of WebEx. Also, if we are unable to answer all your questions within the live webinar, we will answer them later on via email. And if you have any questions left, just email us at digital-v-days@we-online.com. At the end or in the next days, you will also get the link from us to the presentation as well as to the recording of this session, so you can go through all that again if you want to. So then, yeah, you have all on your side. And now I'm happy to hand over to Baptiste, and I wish you an exciting webinar. Have fun.
So yeah, exactly. I'm going to talk to you about board-to-board connector in high-speed signal chain. So there is two items, board-to-board connectors and what is a high-speed signal chain. So I'm Baptiste Bouix. I'm from France. So if you have any problem with the accent, don't hesitate to ask in a question if you don't understand. And so Marcus will be the moderator. Just what has been said before, we can answer any question by email if you prefer, and thank you for your attention during the next 30 minutes. So I'm going to start with a few concepts that are required for understanding the whole signal chain. It's probably most of you will know this. Maybe it will be a reminder. For some of you, you won't know them, and that will be an introduction to this. First, in any electronic system, actually, any intelligent electronic system will have a computing chip. It will be a microcontroller, microprocessor, system on chip more recently, and it will be processing all it gets from a system bus. A system bus will be a big line of communication where a lot of data can transmit. The system bus will be linked to a memory controller that will handle all the communication with the memory, as it's in a name. And then downstream of this memory controller, you will have an I/O controller. I/O controller will handle all the inputs and output of the system, which is not the input and output on the total final product, because I/O protocols don't involve necessarily an external connector. It can also be to an internal peripheral. And some protocols can be found either on a memory controller, on the I/O controller. For example, the PCI Express on some processor, it will be on an I/O controller. On some other, it will be on a memory controller. Then, to understand all this transmission line, we will have two big types of transmission: either serial transmission, where the bits are sent 1, 2, 3, 4, 5, 6, 7, 8, and received in the same sequence over one line of transmission. In parallel, you will send the same 8 numbers, the same bits, over a few lines and rebuild the signal at the end. So it involves a bit more than this, but it's a massive concept. As we see, parallel signaling can, in theory, be much more faster, because you can pass the bits over a number of channel n. So if the channel can pass the same amount of data between serial and parallel will have a throughput n times over. It's not that simple. First, we have limits to this transmission. the receiving chip has to be able to read the symbol. And problem is you send the red line here, you send the red dotted line here, that's what you expect to send. But what you will receive is more like the blue line, which is the slopes are not that vertical. You will have reflection, you will have parasites. There is a lot of problems that arise from transmitting a symbol. If the chip can read anything above the orange line here, then you will be able to read this signal. If the chip can only read what's above the yellow-green line on top, then there will be a problem. You won't detect that bit of information. That's not something that designers take lightly, because this graph here is from the GEDEC about the memory the memory signal length. So this is something that is studied very thoroughly by designers. And what's important is the sample rate. It will be the receiving device, the frequency, the reading frequency of the receiving device. We design it in transfer per second. So in number of symbols you can send over 1 second. And since we are dealing with something related to time, we can also transform this in frequency. Actually, loss are frequency dependent. The higher the sample rate is, the larger losses will be. Why? Because physically, signal chain at high frequency will come from impedance itself. So the resistance of your transmission line to the high frequency signal, this impedance is created by coupling. So here is a magnet. It's electrical field coupling, magnetic field coupling. Sorry, picture on the left. But you will have also problem with impedance mismatch. That is, if you have high impedance then low impedance, you will have some problem. And you have also losses that are related to signal going to nearby conductors that we will call crosstalk. And so connector and cables are source of high frequency losses that we have to check. Impedance mismatch itself is a big issue, especially for designers of devices, because if you have a connector or a component on a system that don't match the impedance of other components on the system, you will have a big reflection. The signal will bounce on the connector, on the component. As you can see on the graph below, if we have a impedance of 50 for the whole system, and then one connector or one cable has a different impedance, we will have a massive reflection. The best transmission is achieved when all the components on the system have the same impedance. So impedance matching minimizes reflection, maximizes efficiency, and that's something that we have to check as manufacturer, but also you as designers. To limit losses, you must match the connector impedance with the PCB. So the pin on connector ends have a different impedance than all the other pins, because they are not surrounded by the same conductors. So it's not advised to use pins on the edge of connectors to transmit signal. But that's not always possible. For RG45 connector, for example, you have to use all the connectors, all the pin on the connectors. So other provision have to be taken. The best performance is reached when a single pin has ground pin around. So we have a few configurations that works for this. For example, the GSG configuration. Then the GSSG is also used. So you have two signal pins right next to each other. They are used for differential signaling generally, and they are very used in higher frequency and noisy environment application. And then you have the GSG, so you have a ground pin around each signal pin, even at a differential signaling. And then you have a very good performance as lower frequency, but as a trade-off, you have a worse performance at high frequency. Then what's important for the qualification of connectors is the Nyquist frequency. And since it's not always clear, I will explain what is the Nyquist frequency. So the Shannon theorem of integrity of information says that to keep the information, you have to sample any signal at twice the highest frequency of the information. A digital signal will be 1 and 0. I represented on the right digital signal with 1 0 1 0. If we sample this, we have a peak, a Dirac distribution at 1, a Dirac distribution at 0, 1 0. Then that's the sample rate. The sample rate is 1 over this time between each sample. If we try to reconstitute a signal that can match, the easiest signal that can match this sampling, we have this weird looking red line, which is close to what we saw earlier with the JEDEC graph. So it's a sloped, vaguely sinusoidal function. And this sinusoidal function has a frequency of 1 over 2 t. So it's a frequency of the frequency is half of the sample rate. It's the frequency, the Nyquist frequency. So the important frequency of the highest digital signal we can pass on a connector is half of its data rate. Symbol rate, sorry. That's why that's something that's sometimes a bit tricky for designers, because you know that you want to pass, let's say, 1 gigabit per second, and then we tell you, okay, we have to pass 500 megahertz. That's normal. It's because the Nyquist frequency of this signal will be half of its sample rate. So the application would be here for the Ethernet physical layer is the categories, Ethernet categories. Actually, Ethernet categories are a definition for connector of losses. Here is a plotted insertion loss allowed to a connector. So every component in the Ethernet cabling system will have a budget, a loss budget in decibels. For example, if you have a 1.5 dB loss budget, you lose about 1/3 of the signal. 3 dB, you lose half of the signal, and so on and so on. You can add these losses on all the components on the signal chain, and this loss budget is generally given by the standard, which is the physical layer. Then we are going to see some of these standards. For the memory bus or the North Bridge, we'll have the DRAM connector, dynamic random access memory, which are used to store the data and the program while the processor is using them. So it needs a lot of data, a lot of capacity accessed very fast, but not too much capacity. You know, you need the biggest challenge in this is to have a high throughput. So the widespread technology is double data rate SDRAM. It's a standard maintained by the JEDEC that goes from DDR1 to DDR5, and which are separate standard for graphic memory, GDDR, that has an even higher throughput. It's a parallel transmission bus, so that means that all the memory channel will have a GSG configuration. So basically, you have a ground signal, then the pin right behind the signal will be another signal unrelated to the first signal. It's not a parallel transmission, but you will have all the signal going through nearby pins, interfering between each other. And especially, it's important because the Nyquist frequency for this signal go up to 3.6 gigahertz. It's high, it's very high, but to give you an idea, it's less than what you can have on a high-tier USB-C communication. The standardized chips are treated like commodities, so it's something that is very common to have. So any designers who needs memory more than what's inside the system on chip will have to deal with this. So it's something that is very common. Another very common North Bridge protocol is a PCI Express used for chip-to-chip communication. It's also a widespread technology that combines power and data delivery. It's maintained by the PCI Special Interest Group and is available on 7 different standards and up to 17 transmission and reception lines. Then it's a serial transmission, so GSSG on every connector. And it goes from, it's a differential configuration, and it goes up to 32 gigahertz of Nyquist frequency. That's 10 times over the DDR. For this application, you see it's a very demanding for the connectors. Generally, you can use board edge connectors, but it's very low. It's very bulky. It's not very adapted for it's only adapted for desktop PC and servers. But for everything that is smaller boxes, that is laptops, it's not very relevant. And same, this is standardized, so it's very useful when you need to swap RAM DIMM, which is what you see on top, or PCI Express extension card, but it's not very useful if you design something that doesn't need this change, this potential change. The alternative is to use a board-to-board connector, of course, because the presentation is called like this. A mezzanine board-to-board connector is possible to be used as a RAM connector or a PCI Express connector. The standard, you see, they are very demanding. Normally, for PCB connector, like we saw, a board edge connector, we only have 1.5 decibel losses allowed at the Nyquist frequency in the PCI Express standard. That is, if you keep the standard configuration. If in your system you have a different configuration, for example, if you solder directly your CPU to the PCB, you can avoid the losses in red in the graph. If you have a better motherboard, you can reduce some of the loss on gray. And if you have a better daughter board, you can reduce the loss in blue. And so you can have a better loss budget for your connector at the sake of interchangeability. So our connectors can be used for this application. They have 100 ohms differential impedance as PCI Express. They are more compact than board-to-board connectors. They have a very limited insertion loss here in GSSG configuration, and they are cross-referenced with other manufacturers, which can help for compatibility and double sourcing. However, they are not standard. They are not in the defined standard. So when you use them, you are on your own, and they have a lower power allowed than board edge connector, which has to be remediated by other means. Then let's go to the I/O signal chain, also the south bridge. I/O signal chain are sometimes much more complex than the memory signal chain. For example, if you take Ethernet, the Ethernet interface that we talked before, you can have as many configuration as you can have as many configuration as there is combination between the RG45, the physical IC, the MAC IC, and the CPU. Sometimes some components are integrated into other, and sometimes not. So as a designer, you have to make a choice if you have only the RG45, if you have a standalone physical receiver IC, if you have a standalone MAC IC, or if your CPU includes all these chips. We are going to talk a bit about the MDI here. MDI is a media-dependent interface. So it's what's inside of the cable, the Ethernet cable that links this tablet here, transmits the MDI. MDI is itself has a very standardized set of losses. That means that the whole signal chain has to have a certain loss budget. So you will share this loss budget between the active receiver, the PCB trace, the filters here, the modular jack, then the cable, then the device 2, the device that you are linked to, will have the same constraints. We know that all the devices that follow the TIA standards that define Ethernet interface, we know that any device on this will follow the same rule. That makes you can plug any device 1 with any device 2 with any cable that respects the TIA, so the category. And I will take an example for this, an example that we have with a customer recently. He had a the receiver chip and the RG45 not on the same PCB. He wanted to have 100 megabit per second, so category 5, and he didn't know how to link both. So he wanted to use a type of board-to-board connector, which is the FFC and FPC. But how can he use this? So he has to use the FFC and FPC. It could have been a mezzanine board connector, but here it was a flat cable. So he used GSSG configuration because that's the same configuration as the signal from the MDI. He has to use at least 13 pins, not over 5 and 10 centimeters, and 100 ohm differential impedance. But isn't there a problem with the Ethernet standard? Because you are adding 0.16 decibel of losses with that FFC and FPC, or around something like this. It's something that we measured. The FFC and FPC adds 0.16 dB. The category 5 G45 has a load loss of 0.32 dB. If loss budget adds, then this device will not respect the Ethernet standard. Well, we had an idea. The customer just had to bump the G45 by one category up with lower load losses, so 0.16 dB for a category 6 G45, and then the whole device, if it has a continuity in impedance, then it will respect the loss budget for Ethernet. For USB high-speed interconnect, it's about the same. That means between two USB hubs, you have a load loss of 24.5 decibels. Generally, we use these decibels for USB connector, USB cable, and then another USB connector. But if you want to use USB as an internal connection board-to-board, internal board-to-board connection, which is often the case, you just have to check that your board-to-board connector here can pass your signal with a total load loss of 24.5 dB. Sorry. And that's also interesting because you can have transmission up to 20 or 40 gigahertz. 20 or 40 gigabits, sorry, and an increased frequency of 10 gigahertz. For other serial protocols, you have, for example, the serial bus SATA, the serial ATA, which is also transmitted in the same fashion, GSSG on a flat cable that you can also transmit with a board-to-board connectors for space constraint. Its increased frequency is up to 6 gigahertz, so it's totally fine with the board-to-board connectors, the mezzanine board-to-board connectors that I showed you before. For I2C, which is another protocol much slower this time, it's used a lot for intership communication, and all these low-speed serial I/O buses can use pin and socket headers, like here on this Raspberry Pi, for example. For parallel I/O buses, you have it's mostly old buses. So for example, you have the EDE or parallel ATA, which is 16-bit wide. You can use ribbon flat cable and box headers as a way to transmit this kind of signals if you still have them. And the compact flash or PCMCIA standard is about the same. You can use the same ribbon flat cables, but if you want, you can also use a card connector like this, which was actually designed for. As a conclusion, when us at Würth Elektronik, we make signal chain analysis, we go from the core of the system and we analyze the different protocol that can stem from a single chip. It's a good way to find which connectors you may need and which new solution we can bring. It's a good framework to adapt the qualification test to give the most accurate information to the customer. And it's a good way to integrate the work with our colleagues, like the one who work on the passives that will go to the rest of the signal chain. It's always interesting to know and to understand the environment, technical environment around our connector in order to propose suitable solutions. So that's why we always like to have some feedback on the connectors, on where they are used. We like our success story also, the more feedback we have, the more we can work together and the more we can propose new solutions. Thank you for listening. And if you have any question, I think it's time.
Yeah. So thank you very much, Baptiste, for your presentation, first of all. So yeah, nice to hear all those information. Of course, now we are here for you, for your questions, and we see already there are some questions coming in. Just repeating, as we said in the beginning, if we can't answer all your questions now in the live webinar, we will answer them later on via email. And if you just have any questions left, just email us, and you see the slide right now with the email addresses you need. So Baptiste, let's start with the first question. Are the Würth Elektronik board-to-board connectors fit or high-frequency signaling?
So for the board-to-board connector that are in low pitch range, they are all fit for high-frequency signaling. Either the 0.8 millimeter or the 1 millimeter pitch, they are fit for this at different loss budget, of course. But yeah, we are going to make a publication of all this frequency data in the next future, so the customer can check. Probably it will be an application note, so the customer will be able to check directly up to which frequency they can add the board-to-board connector in their system.
That's good to hear. So thank you very much, Baptiste, for the answer. Then, yeah, let's go on with the next one. What is the qualification method for high-frequency connectors?
So there is two methods. The one we use generally is we have a virtual network analyzer and we measure the S parameters in the GSG and GSG configuration, as I showed before. So we measure all the losses related to frequency. For products, for customer product, generally it will be more a diagram qualification that will include the whole signal chain. We did that in the past, for example, for USB connectors, but now we have moved to VNA, to S parameters qualification.
Okay, thank you very much. So just in the middle of our questions, also the information, because that was also frequently asked question in the sessions before of our digital V-Days. You will get the link to the presentation as well as to the recording from us in the next few days. So also the slides, you can download them.
Yeah.
So then next question, which I can see at the moment, Baptiste, do all protocol standards have high frequency loss requirements?
So that's a complicated question. No, not all standards are well made, I say. Some standards have high frequency loss requirements that are clear, like the Ethernet standard has clear defined high frequency losses requirements, the PCI Express also, but some other protocols don't have this. Some other protocol, as long as it works, it works. But they are not very good for interchangeability. So some protocols have high frequency losses requirements on components. Some other have on the whole signal chain, and that will be a diagram qualification on this one. And some protocols will have nothing, but just say you will have to be able to transmit 10 gigabit per second, for example. And this one are the hardest to find solution for. I mean, we often have questions from customer about this protocol. Can we pass memory signaling on this protocol, and so on and so on. So that's a bit more complicated than this. Some protocols have them, some others don't have them.
Okay, Baptiste, thank you very much for your answer. And yeah, as we can see at the moment, that's the last question.
Perfect.
So I think that's also a good sign for your presentation. All answers, all questions were answered already. So Baptiste, first of all, thank you very much for your time and for your presentation.
No problem.
Today.
It was a pleasure.
For me as well. So then thank you, all of you who attended now, for your attention. And I hope you enjoyed our webinar, and also stay tuned with our other sessions of our digital V-Days. You know, you can already register for all the other sessions on our homepage. And yeah, that's it from me now. Thank you very much, and have a nice day.
See you.
Bye.
Bye.